Hi students, Ms. Gardner here, and today we're going to talk about intermolecular forces. So I'm going to start this off by asking you a question about oil and water. So why don't oil and water mix? And you might have experienced this if you've ever had salad dressing that you've had to mix together by shaking it. So what's causing that separation? If you first said density, that certainly explains why the water is on the lower level and the oil rises to the top. They have different densities, so they will have different separation, but that doesn't explain why they don't mix. So to consider that, we really need to consider the polarity of the molecules and the intermolecular forces or interactions between molecules in a substance. So let's start by looking at a Lewis structure for both water and oil and really understand which of these is polar and which is not. So if we look at water on the left here, we can calculate the electronegativity difference of an oxygen-hydrogen bond, and that will be 1.34 for an OH bond. All right, so that's a very polar bond. That falls into our polar covalent region of bonding. Now let's compare that with oil. Here you see it's a long chain of carbon and hydrogen bonds, hydrocarbon, and this is a generic representation of oil. This is not exactly what vegetable oil is, but it will be representative for what we need to talk about today. So a carbon-hydrogen bond is a non-polar bond. That electronegativity difference is only 0.45. All right, so that's our first step in explaining this phenomenon of oil and water. All right, so water is very polar, oil is not. So if we consider the direction of polarity on water, we can draw in those dipole arrows. So they point towards the oxygen, the more electronegative oxygen. And then the plus sides of the arrows are over our hydrogens. Okay, so since we have these dipoles here, and because of the asymmetrical shape of water, we have a polar molecule. Those dipoles don't cancel, and you may remember from the comic that we reviewed, this was represented by that polar bear dragging those little penguins. So we can represent the net polarity with this blue arrow here, and that shows basically that all the electron density is being pulled towards the oxygen and away from the hydrogens. Okay, so in summary, water is polar. I want you to have that stuck in your brain. And that means that there's a separation of charge in the molecule. So we can represent that also with these deltas. These are lowercase Greek deltas, and they mean partial. So we have a partial negative charge on our oxygen atom and partial positive charges on our hydrogen atoms. All right, so this separation of charge is what we mean when we say polar. Okay, so we've just been looking at one molecule of water, but in a droplet of water, there's millions of them. So what happens when they all bump up together? Well, they are going to orient themselves in a way so that those positive and negative charges line up because opposite charges attract. So you can see here with these little purple dotted lines, there's some attractive force between the hydrogen of one water molecule and the oxygen of another water molecule. All right, so these are partial charges. They're not like a full ion, but enough to have attractive forces together and see how they line up between molecules. All right, and we can see this pretty obviously with the surface tension that we can see with water compared to oil. So if we tried to stack a bunch of water droplets on a penny, we could fit so many and have this really round bubble that would take a while before it would spill over the edge. Compare that to oil, which does not have these attractive forces. It's going to spill over pretty easily. Okay, so that is a key attribute of our polar bonds in water. Okay, so another thing that we can use this idea of polarity is to explain also solubility and attractive forces. So polar likes polar, and you'll hear me say this a lot, like dissolves like. So here we've got another little representation of water molecules. Here the oxygen is the red sphere and the white spheres are hydrogen. So this is kind of maybe we got a droplet of water here, a lot of intermolecular forces between our water molecules. All right, so polar molecules attract other polar molecules. The shared electrons in a water molecule spend more time near the oxygen atom, less time near the hydrogens, and then that results in these slightly positive and slightly negative regions on the molecule. And this impacts how they interact with other molecules. So these little dotted lines here, they represent something we call hydrogen bonds, which is that attractive force between two water molecules. Okay, so you've heard me say intermolecular forces. So you may also hear intramolecular. So those two prefixes have very different meanings. So an inter versus an intramolecular force. So let's look at this diagram here of some water molecules. So an intramolecular force is a covalent bond. That's something within the molecule. Compare that to an intermolecular force. That is something between molecules. So this red dotted line here is an intermolecular force. So we're focusing right now on intermolecular forces. We've already talked about these intramolecular forces. Okay, so there's a couple different kinds of IMFs, that's how we abbreviate that, intermolecular force, that we are going to talk about today. So the first type we'll talk about is an ion-dipole interaction. And not surprisingly, this happens between an ion and a dipole. And we learned that a dipole is just another word for a polar molecule. So here we have a sodium ion, right? It's a metal. It's lost one of its valence electrons, so it is positively charged. And these are some water molecules. And the positive ion is attracting the negative region of our water molecules, and they're all going to line up kind of in this way. So that is an ion-dipole intermolecular force. Okay, we can have another type of force called a dipole force. This is happening when we have polar molecules. So polar molecules, again, those are also called dipoles. The example here is HCl. Here we have a strong separation of charge. The partial negative charge will be over chlorine, partial positive on hydrogen. So all of these molecules, when they bump up together, they're going to orient negative, positive, negative, positive. And so that is our dipole interaction here between two polar molecules. All right, I already talked about the intermolecular forces of water. That counts as a dipole-dipole force, but it's a special kind because this oxygen-hydrogen bond is so polar. It has a really high electronegativity difference between those atoms. So hydrogen bonding, special type of dipole-dipole, we see that when we have molecules that have OH, NH, or FH bonds. So just those three scenarios. So when you see OH, NH, or FH, think, oh, there's some hydrogen bonding happening here. All right, so we can have all of these things happening in one substance. So here we have, let's see, this is methanol. We have a region of methanol, the hydrogen-carbon region, that is kind of nonpolar. But then the oxygen-hydrogen region and the oxygen-carbon region, it has some separation of charge. So there's some polar character in this molecule. So we can have hydrogen bonding happening between our OH bonds. And then we can also have just dipole-dipole interactions between our separation of charge in there. So we can have both all together. All right, the next type of interaction we can have is called Dipole-Induced Dipole. And this is between a polar molecule and a nonpolar molecule. So think back to our cheerleader states of matter, if we've done that in class, but just remember that all particles, they're always moving. They're always moving a little bit. And even if we have a nonpolar molecule, it's still going to be moving a little bit, and we can have some electrons kind of shifting around. And if we have polar molecules nearby that have their separation of charge, they can cause an induced dipole. They can induce a dipole. by having their, say, negative region of oxygen kind of bumping up near an atom, and then maybe some electrons shift around. So this is a polar and a non-polar molecule. So this is a pretty transient interaction, but still definitely present sometimes. All right, and then the last type we're going to talk about are called London dispersion forces, and you can certainly abbreviate that as LDFs. So London dispersion forces are always present. They are weak, they are temporary interactions, but they are just a product of the fact that molecules are always moving. And, you know, if you imagine these molecules are all at a dance party and they're dancing around, and maybe one of them's trying to hold a drink, and someone bumps into someone else and you get off balance for a moment, right? So that's what's happening with just any old molecule. So if we have a bunch of non-polar molecules, there's still going to be some temporary attractive forces between them, just from them bumping around into each other. All right, so London dispersion forces are always present, even with these very non-polar molecules like Cl2. Okay, so I might ask you a question like, what intermolecular forces are present in this mixture of water and O2? All right, so if water's there, we are definitely going to have hydrogen bonding. That's already shown in with my dotted pink line. All right, we've got water, a polar molecule. We are also going to have some dipole-induced dipole. O2, that is a non-polar molecule, right? It's very symmetrical. There's no electronegativity difference between the oxygens. But it's going to be bumping up next to some polar molecules. It might temporarily feel a little polar. All right, and then London dispersion forces, those are always going to be there, just from the random motion of molecules. All right, so we could represent 3 different intermolecular forces happening here. All right, so to summarize all of the intermolecular forces, we can have ion-dipole interactions, and that's between a polar molecule and an ion. We can have dipole-dipole interactions, which is between 2 polar molecules. We can have hydrogen bonding, that's a specific type of dipole-dipole. And we can have dipole-induced dipole, so that's when we have a polar molecule and a non-polar molecule. And then last, we always have London dispersion forces. Those are always present, and they're weak and transient. All right, and last thing we're going to talk about is really how can we compare these? Which are stronger forces, which are weaker? So there are quite a few charts out there that you can find that will measure the energy of these interactions. So this chart here, I'm looking at this column energy, which is in kilojoules per mole. So an ion-dipole interaction is going to be the strongest of these IMFs, right? The ion, that is a fully positive or negative charge. So that will have a higher attractive force. All right. From there, hydrogen bonds are going to be pretty strong. That's such a dramatic electronegativity difference in atoms that that will have a strong attractive force. Then dipole-dipole, ion-induced dipole, dipole-induced dipole. We didn't really talk about ion-induced dipole, but similar to dipole-induced dipole. And then London dispersion forces are the weakest. All right. I definitely noticed some charts, they kind of switch the position of hydrogen bonding versus dipole-dipole. But for what we're going to talk about, we're going to consider hydrogen bonding to be a more attractive force. All right. If you have any questions, please let me know, and have a great day.